has, if you can see, one electrode on one side and two electrodes on the other side. And in between those electrodes, you have a thin layer of semiconductor. So this is a field effect transistor. Source gate, source drain, gate. Okay.
Okay. So thank you for having patience. I have started recording. Welcome everyone to the Quantum Journal Club. We have 6 members here and a few members online. And I'd like to thank Dr. Alexander Gumennik for agreeing to present. And also thank you, Professor Ortiz and German, for joining us today.
Should I share the screen?
Yes.
Share the screen. Share. Okay. And I probably should hide. I don't know if I want to hide the panel or just transfer it to a different screen. Okay.
So we would have wanted to say a few words about you, but then we're going to end up saying just a few words. Number one, you are an assistant professor of intelligent systems engineering. Number two, you are the director of fibers and additive manufacturing enabled systems laboratory at the Department of Intelligent Systems Engineering at IU. The idea behind this relatively difficult or strange setup is that a group of, we set up, as you know, the Journal Club for students in quantum information science. We are busy recruiting more people, and this is a hybrid setup that is a little bit unusual. There's a group of 6 or 7 together in Ladi watching this, and then there are a number of us online. So with this, what can you tell us about FAMES?
Okay, you saved me 5 out of 15 minutes by this introduction, which is very generous of you. So maybe I will have 5 extra minutes in order to explain the technology. If any of the students took E500 class, then maybe there will be overlap between what I'll be talking about, but not a complete overlap, because E500 is an intro into research for the engineering students. So at least technology is the same. Technology intro is the same technology intro. Fibers and additive manufacturing systems enabled lab, FAMES lab, is designed for a design, material processing, manufacturing, characterization, and integration of active fiber devices into systems. And when I say active fiber devices, I mean fiber devices that, for instance, have 5 senses and stimuli of a human packaged into a fiber, and then later can be weaved into a fabric form factor. So normally in that technology space, what people are looking for is, for instance, to design textiles like the t-shirts of the kind that you guys are wearing, to be able to, for instance, sense that the wearer is stressed and then provide a stimulus, for instance, in the form of massage. Okay, so you can imagine one fiber sensor that monitors physiological expressions of stress, like heartbeat, sweat, breath rate, and another fiber that is capable of contracting and expanding, and you have a feedback system between those 2 fibers, and you are capable of sensing a parameter and then providing a stimulus according to what you sense. Another example of active functionality would be a fiber that has data processing capabilities. So in that case, you want to take something passive as an optical fiber. An optical fiber is ideally a passive device. It transmits a bit of information from point A to point B, ideally without any manipulation. With the same amplitude, with the same frequency signature, with the same width in time. You want that pulse of information to be transmitted through the fiber and received exactly the way it was sent. Ideally passive device. We want to take that and to transform it into something that is capable of data processing in a similar way as microprocessor. So normally an optical fiber, which is just a glass thread, of the kind that I have shown you prior to the lecture, we need to make a few changes to that thread. We need to, first of all, package multiple materials that would provide the active functionalities that you desire in your fiber device. For instance, semiconductors, insulators, or nonlinear optical materials, piezoelectric materials, and so forth, in geometry that would correspond to the device with the functionality that you want, at the length scale that is typical to the state of the art in this realm. So if we are talking about data processing with microprocessor, you need to control your architecture on the level of micron and submicron. So in order to attain that, we develop something that is somewhat similar to what is known in microelectronics industry as very large scale integration. That's a design and manufacturing approach that enabled the modern microprocessor the way we know it. And in this technology, there are ways to control the architecture of microprocessor in all 3 dimensions. And we develop a control over the architecture of materials arrangements inside the fiber in all 3 dimensions. So we start with 3D printing the cladding of the fiber preform. That's the glass that provides the matrix of the structure. We fill it with materials that are active materials, for instance, metals and insulators in that case, at the geometry arrangement that we want in the final device. Okay, then we take this thick and short rod, dip it into the tube furnace, heat it up to a state of a viscous liquid until it glows white and drops down, carrying with it a thin strand of a fiber. We grab on that strand of a fiber and draw it very fast on the bottom. And if we design the combination of the materials properly and catch the sweet spot in the processing parameters of the fiber, such as draw temperature, which defines the viscosity and the tension of the draw, and the rates, speeds, right? So molten glass is a non-Newtonian liquid, so it will experience different stresses at different feed and draw speeds, regardless of the fact that the ratio between the feed and draw speed is the same. Obviously, what defines the scaling factor of the geometry of the cross section is this ratio between how fast you feed the material into the furnace and how fast you draw it out. You have a volume conservation, so give or take, your scaling factor will be a square root of the ratio between the feed speed and the draw speed in terms of the final radius of a fiber compared to the initial radius of the preform. So if, for instance, you have a centimeter thick preform and you want a fiber that would be 100 micron in thickness, you have a scaling factor of 100, okay? In terms of speed ratio, it has to be a ratio of 10,000, and it also means that the scaling factor in length is 10,000. So if you get a preform 1 centimeter thick, get out of it a fiber of 100 micron, and your preform was a meter long, the fiber will be 10,000 meters long, which means that from every meter of a preform, you get 10 kilometers of a fiber. And in that fiber, all the structures are scaled down by a factor of 100. So if you had a wire that is millimeter thick in the preform, it will be 10 micron thick wire in the fiber. And it is possible to scale down by a draw features and the macroscopic features in the preform to sub-micron level of feature size in the fiber. And those features will be submicron in cross section, but will span the whole 10,000 meters of a fiber. So that's a control over 2 dimensions of the cross section of the fiber. But however intricate, however complex the cross section of a fiber, it is still axial uniform structure. So we need to find a way also to control the 3rd dimension of a length of a fiber. And that we do by a post-processing step, which is based on local amplification of capillary instabilities. So let's say you have 2 semiconducting cores surrounded by 2 metallic cores. And those semiconducting cores are p-n doped silicon. Okay, and you can reheat the fiber locally by a hydrogen oxygen flame or by a laser spot, such that a short section of semiconducting cores is liquid, and then feed the fiber through that hotspot. Okay, and what you will observe is a capillary breakup that is very similar to how water drips from a faucet. It will have droplet by droplet liquid core forming at the tip of the continuous section of a core and detaching, and you will end up with a periodic structure of bispherical entities. So sphere that detaches from a core that is broken up by the capillary breakup process is always larger than the diameter of the initial core, because it collects material from certain lengths of a breakup period. So you can design the distances between initial continuous cores such that those droplets, when they detach from the continuous cores, they will touch each other and electrodes on the side. And you end up with an array of p-n junctions contacted in parallel. So that would result in an array of photodiodes contacted in parallel by 2 metallic electrodes. You can also design a solidification process past the breakup in such a way that it happens along certain temperature gradient. So for instance, if you look at the sphere that exits this hot zone of a flame or a laser beam, it will experience lower temperature with a pole that is farther from the flame, now on the way out of the flame. And that's where the solidification will start. Now, usually, if you have a semiconductor that is doped with some material, solubility of that dopant would be different in liquidus compared to the solidus. So for instance, if you have germanium inside silicon, germanium is more soluble in liquid silicon than in solid silicon. So if a mixture of silicon and germanium solidifies, the solidification process will extrude most of the germanium into the remainder of the liquid as the solidification progresses. And you will end up with heterojunctions of silicon and germanium. One side will be germanium rich, one side will be silicon rich. So we have realized a library of devices using this manufacturing approach, from photoconducting photodetectors contacted in parallel in germanium, silicon germanium heterojunctions, p-n junctions and p-n doped silicon. And also, since the process is miniaturizable down to submicron scale, we have shown long-range periodic structures, photonic, one-dimensional photonic structures in fibers. So that's pretty much the technological procedure. Now, it took about 15 minutes to explain, and I would like to, do I have 10 more minutes to explain how it's useful for quantum networks?
Yes, and the thing is, we just need to end basically at 7:55. That's all.
Okay, so this is useful for quantum photonic applications, because if you look into any quantum photonic circuit, you will see that it's a combination of guidance structures, continuous guidance structures, and resonance structures that concentrate photons to the extent that they are capable of interacting with each other. Photons are bosons. Normally, they don't feel each other. They can be at the same location with the same energy at the same time without interacting. Okay, so to make bosons interact, you need to concentrate them to the extent that they interact with the material inside which they are concentrated, and that interaction with the material changes the properties of the material in such a way that the next photon that comes in feels that change of the material. So interaction between photons has to be mediated by nonlinear optical effects inside materials in which photons interact. So any photonic circuit is a guide to a place where photons are resonantly amplified in order to make the changes to the material that allow them, mediated by that change, to interact with each other. So it's a combination of waveguides and resonance structures. And resonance structures are created by those photonic gratings, okay? And waveguides are just continuous cores. So since we can create waveguides and can create resonance structures, we can create any combinations of those. And advantage of fiber draw process, one of the advantages of a fiber draw process is that any material that is liquid at the draw temperature of the glass, which is 2000 degrees, if can be kept from chemically reacting with silica, can be drawn into a core. So that's different from what you find usually in silicon wafer processing, or in germanium wafer processing, or in 3-5 semiconductor wafer processing. In wafer processing, you start with a substrate material that is well defined, and any device that you will get out of the processing, CMOS compatible processing, will be a device that is a derivative of a substrate material. You're limited, in other words, to a specific material platform. In fibers, you can combine any materials in any combination of cores, as long as they are liquid at 2000 degrees Celsius. You can cram them all into one fiber. You have a bunch of other material science challenges that are related to the fact that you are trying to create solid state devices by liquid phase processing, and liquefaction and solidification are inherently uncontrollable processes. So in order to control them, you need to develop the whole separate body of material science, which is what I'm trying to do. So it's more like a problem that it's a solution that seeks multiple problems. But nevertheless, that specific problem of being material agnostic, the fiber processing does address. Okay, so applicability of this to quantum network is coming from the fact that if you look into quantum network, you have usually multiple material platforms, each of which corresponds to a different mode or a language of electromagnetic energy distribution that this platform is talking in. The more so, every platform will have information encoded in physically different manner. So you have, for instance, ionic qubits, you have qubits on neutral atoms, you have qubits that are in superconducting rings in the form of Majorana particles, in the form of electrons, in the form of RF frequency photons. So physically different qubit implementations. And you need to have links that would link the nodes in such a network that are capable of translating information that is understandable by one node into the form of information that is understandable by another node. And if you look into current digital communication workhorse, which is that optical fiber, it's just a simple thread of glass. It doesn't have any data processing capability that is needed in order to perform such a translation. So we are trying to package this translation capability into the fiber. And that translation has to be made with very high efficiency. So if you look into designs of commonly proposed integration schemes of quantum networks, those ELUs, which are elementary logical units, at least theoretically has to be able to communicate to each other with very high efficiency, such that, you know, a qubit in the form of one single photon emitted by this ELU makes to the processing matrix with probability of 1. You can't allow any losses. Okay, so for instance, if you look into what is required from those links in the quantum network, one of the things that you need to address is mode conversion. In long haul communication fiber, optical fiber, your electromagnetic distribution of energy is a Bessel function. So it's circular symmetry. On the other side, you might have some material platform. For instance, you can have a photonic crystal fiber that traps atoms inside. That fiber would have 6-fold symmetry of a mode. On the that's on one side, outbound platform. On the inbound platform, you might have, for instance, a silicon photonics chip. In silicon photonics chip, you have a Rib waveguide, which has rectangular symmetry with high refractive index on the side of a wafer, so it draws the electromagnetic radiation towards the high refractive index. Effectively, you will have a trapezoidal symmetry of a mode. Okay, if you just brute force try to couple circular mode, if you try to couple square peg into round hole, not all of the peg will make into the hole, right? So you need to reshape adiabatically the peg into the shape of the hole that you are trying to fit it in. So it fits. So basically, you need to have some kind of a fiber, which on one side looks like a 6-fold, on the other side looks like a circle, in order to couple the mode from atomic trap to the long haul fiber communicating cable, and then back from the long haul communication cable into the silicon chip by adiabatically changing taper that translates circular mode into trapezoidal mode. That's not something that current fibers are designed to do. Another thing is mode conversion, is qubit conversion. So we have been talking about, for instance, ionic processors that need to be coupled to each other through photonic links. Okay, so if you look into ionic processor that is inside a pole trap, due to the shape of the trap, that cannot be too shallow, otherwise the ions will escape. Okay, because you have Coulomb interactions between them that repel them from each other. You need basically the bowl to have high enough of walls in order to trap the ions in, because they want to repel each other. So you can't trap more than a few tens of ions at once. So your ionic processors are limited to a few tens of qubits. If you wanted them to scale up to be able to perform complex tasks that require thousands or millions or billions qubits, you need to have a very high efficiency scheme of translating information from one, communicating it to the next one, and coupling it to the next one, and translating it back into photons, coupling it to the next one. So you need multiple traps with very efficient optical links. And that's one of the things that we plan to do with our fibers. So that would be a translation of ionic qubits into photonic qubits, back and forth. And then in the network itself, you also need to have routing capabilities. And this is a very long haul effort because this is not just a quantum switch. That is a full-fledged circuit that has time delay properties. So it has quantum memories. It has a amplification properties. So it has to have qubit sources. It has, and then it has switching properties. So it has to have gates that would route information one way or the other way. So it's a full-fledged photonic circuit with all the capabilities of photonic circuitry, including sources, memory elements, switches, and readout. So that would be the lowest hanging fruit. Okay, that can be done with just very intricate 3D printing of preforms, as I will show. This is a longer haul effort, qubit conversion, but nevertheless relatively simple. And full-fledged quantum photonic circuitry in the fiber is something that is long haul effort. Okay, so how, for instance, do we make mod converters? 3D printing can 3D print any cross section. So if we print something that has a cross section that changes, for instance, from circle to a rib, or from a circle to a honeycomb, we adiabatically along the preform change one shape to the other shape, and the more so if, for instance, we start with just a rectangular preform and draw it into a fiber. Draw process is a liquid phase flow, okay? And as a liquid phase flow, it has two competing forces. One is viscosity, which is there to preserve the shape, and another one is surface tension. And surface tension wants to basically minimize the surface of the volume that you are drawing into a fiber, and this minimization ends up rounding everything into cylinders. Okay, so if you draw at low temperature, you will preserve the shape because the material will be very viscous, and you will end up with a rectangular fiber. But if in the draw process you raise the temperature slowly, you will end up eventually with a smoothened cross section into a cylinder. So here you have, just by change of the temperature during the draw, an adiabatic transition from a rectangular shape to a circular shape. Okay. First attempts to create pole trap in the fiber looks like basically a draw of a quadrupole of electrodes inside the fiber. The next step would be to take that fiber to etch a small gap and then heat it up in order for the surface tension to reliquefy the caps into something that looks like micro lenses. Okay, and then you have an optical core with a micro lens in the end, with a pole trap that is capable of trapping an array of ions co-oriented and in line concentrically with the optical core of a fiber. At least theoretically, when you look into cylindrically symmetrical waveguides for the basic mod, for the basic guided optical mod, there is no cutoff in terms of a thickness of a core. So at least theoretically, if you have even a 1 atom thick needle, it will be able to guide at least one optical mod. So it's a matter of perfect alignment, but at least theoretically, you have a continuous waveguide here, part of which is just an ionic array. So you don't have any free space optics challenges like in normal ion trap, where you have large lenses that need to couple with very high efficiency, something that is limited by a diffraction limit of a wavelength, at least few hundreds of nanometers, into a cross section of an atom, which is few angstroms wide. So the efficiency of such a coupling is extremely low. And you need your efficiency of coupling from photons to ions to be 100% if you want to couple multiple processors, information from multiple processors into one calculation scheme. So we hope that integrating ions into the fiber, into the fiber such that they are part of the waveguide, will allow us to increase efficiency of interaction between photons and ions. Coherent interaction, quantum coherent interaction.
So ions will be flying qubits through the fiber?
Ions will be stationary trapped in this pole trap.
Stationary.
So,
okay, thank you.
So here you have a pole trap that is 4 fins. Okay, this is the pole trap. Okay, and the same idea is here. You have 4 electrodes, 2 of which are AC and 2 of which are DC. Okay, so RF is rotating between 2 crisscross electrodes, creating this rotating well that traps the ions. So rotation in that case is like, if this is the optical core, rotation of the field is like that, the trapping is along the core. So it's a little bit of like sensitive scheme, you know, you really need to design it to be exactly symmetrical such that your trapping is exactly in line with an optical core. But if you succeed to do that, then ion array is part of the optical core. You don't couple light in and couple it out. It always propagates along the same core.
Okay, thank you.
And then first attempts in creating integrated circuits, so you need to draw multiple materials inside one fiber. So this is an example of drawing semiconductor and metal in one single fiber, and then breaking the semiconductors selectively. And that results, here is a core of vanadium, here is a core of silicon, that results in spherical spheres of silicon, which is material that is transparent to 155 standard telecom wavelengths, with a flanking vanadium electrode that if you apply voltage across, you will change the concentration of charge carriers inside this silicon, and change in concentration of charge carriers is expressed as a change in refractive index. So you have spherical resonators of silicon with flanking electrode that can tune the resonant frequency of the spherical resonator. So you have an array of switches, of tunable switches, tunable resonant switches. Okay, we mentioned that you need resonators in order to make photons to interact. So this is an example of such a tunable resonator. This is just a picture of how it looks when you feed such a fiber through a hydrogen flame in order to break up the silicon selectively. It starts from 2 continuous cores and ends up with 1 silicon core breaking up into a periodic structure, and vanadium core stays intact. So that's a special property of vanadium, because vanadium's melting point is 1910. So at the draw temperature of the fiber, which is 2000 degrees, it is liquid, so it is possible to draw into a core, but the breakup, which can be done anywhere above softening point of silica, which is 1650, in that case, breakup is done at around 1800 degrees. So vanadium stays solid while silicon is liquid, and silica around the silicon is soft enough in order to reshape when the silicon breaks up. That ends up being a selective process, material selective process. Okay, so this is just a couple of videos of our biggest ticket item in the lab, which is the draw tower. And as I said, when you have the preform at the draw temperature, 2000 degrees Celsius, it glows white, so it looks like a Christmas tree. And you have a fiber that you need to coat with polymer and then cure with UV lamp. So the end fiber is glass coated with cured polymer. And this shows the reel where the fiber is collected. So that's the end of what I wanted to say. we have a very good virtual tour in our lab. If you want me to walk you through the lab, I can do that. I can address any questions that you have. You're welcome to ask.
I put a question in the chat with a quote from you from 2021. Could you comment on that? And then, of course, anybody who's present over there, they could ask anything they want.
I need to understand whether they implement the silicon qubit optically in some kind of resonator. In that case, I can make tunable silicon high Q factor resonator and fiber, and they can be relatively easy implemented by photolithography on silicon chips for sure in Purdue, likely at IUPUI, most probably not at IUB, most probably not at IUB by photolithography. Yes. Can you give us a more pointer and or info with respect to places at IU, IUPI, or Purdue where such approaches can be pursued, hopefully by members of our student club in cooperation with people and those places as well. So as I have demonstrated, there is an approach to creating resonators in the fiber. This is a very exotic approach, which the places named here don't pursue. They don't have the infrastructure that allows them to pursue that. It's a very special infrastructure that is typical of fiber optic facilities rather than microelectronic facilities. Purdue has very strong, very well-equipped microelectronic facility. They have a couple of tens of thousands in area clean room with extensive CMOS fabrication capabilities. And definitely those can be outsourced there. Most of the silicon photonics can be even done with external companies. So you have external foundries where you can just send a design and they will fabricate it for a small price. So in terms of silicon photonics, this is so well developed that you have bureaus, external bureaus that are capable to just implement the design that you provide. Some advanced technologies like using single electrons as qubits in highly purified silicon is something that is currently in development in Intel. I don't think it is available for fabrication anywhere around the mentioned universities, not because they don't have photolithography and surface patterning capabilities, but because they don't have technology for purifying silicon of the isotopes of silicon. So silicon 19, I think silicon 19. Yeah, silicon 19 is usually at some percentage within normal silicon, and in order to operate electrons as single qubits of the distances that allow interaction between them with high enough quantum coherency, you really need one isotope silicon, one single isotope silicon. And only Intel has this knowledge as far as I know. Any further details that I missed?
I have a question, Alexander. I mean,
yes.
I would like to have some update on the fiber pod trap. So, I mean, as a matter of principle,
Mm-hmm.
I mean, it's not obvious. I mean, in principle, yeah, you can design that thing, but it's not obvious that this can act as a trap itself. So, meaning that, you know, the value of the electric fields that you may need to hold ions in that thing can be so big that you may melt that material inside the fiber. So is it hard? Because you already put, you already draw, I mean, at least you show here and you show, as you know, before, okay, the electrodes, the metallic electrodes, is it hard to draw at least, even not a very long, maybe, I don't know, maybe something like 10 centimeters or 20 centimeters. Yeah, there we go. So where the only thing you do is just you create this pole trap there. Okay, let's say 1 centimeter wide, 2 centimeter wide. And one can try to put some electric fields on the other side and see, if you put in Fields lab, whether some, it's enough to trap. I mean, of course, you have to do the calculation. I understand that. But you can trap some ions in that thing. As a matter of principle, because this looks like science fiction in the sense that, I mean, yeah, sure, I can draw that thing, but, if the electric field that I need melts the metal, is not practical.
If you look at this cross section, it's quite beefy. So as you can see, it's 1 millimeter wide. And the electrodes here are of the order of 70 micron each. So it was like it, and it's not because I don't want to miniaturize it. It's because when I asked Phil for typical dimensions that are needed in order to meet the functionality, those are the dimensions for the distance between the electrodes and for the impedance of the electrodes that he asked me to fulfill. So
yeah, no, I know. But what I'm saying is, I'm seeing that you put the electrodes. What is missing is to get this empty, I mean, get this empty, open pole trap. Now you take this device, whatever it is, you take that device, you take into Fields lab, you put inside,
Yeah, we were invited for an eager proposal after proposing that as a concept, and it's already 3.5 months in review. So you know how eager proposals go. If you suggest a concept that
this is science. I mean,
right.
This is science. I mean,
we want to do that. Yes, we want to do that. We just need this. We just need a good student that would make an interface between the two labs, would draw the fiber, would etch it, would reflow it, and would go to Phil's lab and
right. But this is what Adrian was asking. I mean, for the different question, Adrian is asking a similar kind of question, not for silicon, but now I'm asking for this pole trap.
Yeah.
Right.
So the answer is that it was designed and fabricated already, taken into account design considerations for functionality. So my assumption is that when Phil said you need electrodes at least 70 micron thick, it is capable of bearing the current without melting the electrodes.
Right, but let me tell you something. Do you realize that if this can be converted into a practical pole trap, you can sell these things in every, as a company, you can sell these for every place, every university.
Yeah,
because it's very simple. You get the thing, you put it there.
Yeah, plug and play qubits.
Yeah.
I hope that it can be done. I don't know. Since
this is the point.
You understand that if it qualifies for eager, it's high risk research. So it's not only you. It's everyone acknowledges that it has more than one technical challenge to be successfully realized.
I understand. But my point is that as a matter of principle, this is something that can be interesting. It will have, a lot of impact. And this is something that a student can do easily. Easily in principle, I mean, do it. I mean, if it works, it's a different story because there are technical challenges, of course. I mean, if it works as a pole trap, that is a big question.
It's a question of a student at this point.
Yeah, so we need to, that's what we're doing. We're trying
more than anything else.
recruit people and find people that could possibly make the connection between the labs.
Yes. It has to be a very good student that on one hand would be very hands-on in order to draw such a fiber because this is a first attempt, so we have this, but there are multiple challenges with the uniformity and the residual stresses and the cracks that develop in silica due to residual stresses over time, and with the uniformity in lengths, with the uniformity between electrodes. Like, there is some optimization that this configuration still needs to go through in order to become functional. So that student on one hand needs to very well understand the ionic traps and quantum physics and quantum information related to ions, and on the other hand be very hands-on to the extent that they can be called a craftsman, a glass blower. Okay, that's almost an artistic work to fabricate such a fiber.
So it could be a dynamic duo, two students.
Can be a dynamic duo, yes. One has hands-on skills, another one has deep understanding of quantum
Right.
information.
Well, hopefully we're getting closer to 7:55, but this was an unbelievably fascinating lecture. And we are going to start pursuing people who might want to just learn about this and see if we ever find that student or students that could help with this.
I'm in mesh, my door is open.
Okay, good.
Thank you.
And Arpan, over there, anybody has any questions? We have like 2 or 3 minutes left.
Anybody questions?
I don't think so.
No? Anybody online?
If not, I'm unbelievably grateful to Professor
My
Gumennik.
pleasure.
Yeah.
My pleasure.
And I'm so glad we recorded this. We are going to share with everybody who couldn't make it today. And we look forward to the future. Thank you so much.
Thank you and have a good night.
Good night. Thank you. Bye-bye.
Thank you for joining.
Yeah. Arpan, so don't forget to stop recording properly and then post it on YouTube. Then I put a link. This was beautiful.
Yeah.
Okay.
It was great.
See you later. Thank you. Bye-bye.
See ya.